Maybe this, or maybe here. Okay, now it's working. Yeah. Hopefully everything is working. Please start the record. Okay, is it started? Okay. Hello, good morning to everybody. I'm glad to proceed. So on our previous lecture, we derived the sort of semifinal system. While I name it semifinal because it's just for some very general form. But to solve some particular problem, we should specify somehow some things which is we will specify here. We could actually specify concrete hydrodynamic instability which work with the convection, because we in our previous formulation, when we formulate the full system, we didn't specify what is the concrete form of all the terms which are responsible for setting on the convection and developing it. So actually the source of the convection, precise source of the convection in precise form, was not determined yet. So let's now just finish this work by definition of this model. And so we proceed to the next chapter, which name is 4.3. Convective instability. Stability. I will abbreviate a little bit. And the final system. And the final system. So we now will derive the final system, because it's actually natural to define the convective instability from the stationarity V equals 0 solutions. Actually, you know that when V equals 0, actually the very essence of all this stuff is that we are looking for the solution on the condition that V is 0. It's easy to see that this solution under this condition is not 0. It's some hydrostatic equilibrium. And namely this hydrostatic equilibrium, it's allow us to drive the convection. So actually we take the initial system. I just remind you this initial system, it consists from 4,4A. So we apply this condition to the initial system, which consists from 4,4,8, 4.7, all possibilities, then 4.6 A and D, A to D, and also it consists 4.3 B. So we apply this condition, just this condition, and we look for the solution which further will be indicated by the 0 index. So without loss of generality, initial accuracy, see the previous section, and taking into account the limitation of our knowledge about the deep interiors of planets and moons, we will agree to consider the adiabatic density, temperature, and volumetric density to be constant. So we just first additional simplification, when we put first, of course, we put the V equal naught. Then we suppose that the volumetric heat density and temperature, adiabatic temperature, and this heat flow are all constant, just for simplicity. R, T, Q. We just name it without any notation, but we should understand that this is the adiabatic value. And this is actually constant everywhere, but except for those places in this equation where significant derivatives are taken from them. So actually we combine this value from some constant value and with some additional derivatives, which we will estimate these derivatives and gravitational acceleration, determining them in the following way, which is in good agreement with all available studies of planets and satellites. So we just suppose that there is some initial constant, and on top of that there is some variable. So we just suppose that, like it's written here, that direct variable in R, because here when we consider this solution with V equal naught, it's spherically symmetric solution. So this spherically symmetric solution has a property that its first derivatives of the adiabatic density divided by dr is equal specially introduced value rho prime, that's simply the derivatives, to distinguish it from the more usually used rho dot over dot. You know that rho over dot is the actually derivation in time, and to distinguish it from the radial derivatives, we put here just prime, and this prime will further mean that this is derivatives. And also in the same fashion we determine adiabatic temperature gradient in R. This is the only distance we have. So, and it's equal, it's more convenient to determine, because actually for density we should take into account the first derivatives, but for the velocity for the derivative from the adiabatic value, we should take actually, because of this form, we should take the second derivative. So the free constant here, another free constant, this is constant. This is sort of the free constant which drives the convection. And the similar free constant here is slightly different. It's rely on the second derivatives on R. And this is more convenient form in the true way to estimate the derivatives of the temperature. And in the slightly another way, we can estimate the gradient of gravitational potential, which is just directly can be represented via the vector of gravity vector under the area where it's walk. So here it's index O, not 0, but O, which denotes the situation, and also it has a component directly in the spherical radius, so we put it here. And this is just to relate them, that this R component, when R is equal RO, we have exactly the gravity acceleration, which is of course down. Not up, but down, because mass usually gravity acceleration. And here the positive constant rho prime characterizes the radial stratification of the density. And tip double prime also free constant, which we fit to particular planets, to our Earth or whatever we have. This constant characterizes the radial non-uniformity of the adiabatic gradient. Both of these quantities are determined by the linearly varying with a spherical radius, gravitational acceleration gradient u minus gradient u originally. So, but here there is another sign because we put it here. And so, of the liquid spherical layer in the deep interiors on planet and their satellite. So the general stationary solution of all these equations, which are listed here, so it's have a general stationary solution, which depend only on R. And actually, we can even write down the equation which we solve, but we didn't solve them, but show what is the equation. Let's start. So first equation is for A. I will see it here. You see that this equation for A, of course, the most important equation, it's Navier-Stokes equation. And it starts from the velocity, but there are different contributions of the velocity. And this velocity, of course, because we suppose that the velocity is zero, we're looking for the solution, for the hydrostatic solution. So this all velocity are cancelled out, but what remains? We just write from formula for A, we have the consequences under the condition that V is not. Then we have that all the velocity cancelled, and then we just could rearrange it in the form entropy alpha T adiabatic over the Cp grad UA. This is one term. And another term, of course, pressure, modified pressure, of course. I just place it in another part of the equation to make it symmetrical. So eventually this look like that. Gradient of the original pressure, or more precisely deviation from adiabatic state, and deviate by rho adiabatic. And also there is a deviation from the adiabatic state for the potential. So we have this equation where when we using V equal naught. Then the next equation is for 7. Just look. For 7 equation. This equation for 7 again under the condition that it's constant and independent on where. The condition that from 4, 7. Okay, we start from A, 4, 7, 8, under the condition that velocity is not, and there is no dependence on the time. I just wrote it like that. So it's easy to see that all these things are completely remove the substantial derivatives. And only things we are left from this equation is that, okay, instead of substantial derivative, we have not. Just stress it that it's not, not O. And it's equal to this term on S plus Q A rho A T A. So this is the second equation. Then we proceed further. Equation, for 7, there are 2 equations. But the second equation quite trivial because we have velocity equal naught. So actually we have not equal naught, so nothing to write down. Okay, so and then there is 4.6a to d, 4.6a to d. And this is just boundary condition. I will not write down them, all these boundary conditions, because you rather well know. And from this boundary condition, we use only two conditions. In this equation, this is condition of the input and output flow, and it's quite important. For another boundary condition, we don't use them because we just suppose that velocity is equal naught, and also there is actually no need to use the boundary condition here because here the solution is quite simple. And finally we will have, okay, sorry. So this general solution of V equal naught, solution of those equations which are listed here, can now be easily obtained. From it, we immediately isolate the further required sources of convective instability S prime and the time derivative of the adiabatic entropy as we clarified in the formula for 3b. So, which is actually integral condition, additional integral condition, just to help us to utilize this equation. So I will not show you the intermediate step, how we solve this system. It's relatively simple, but you can repeat this as your exercises. I just will write down the result. And the result is as following. Okay, maybe. Here it's listed on the blackboard, but here perhaps I will, okay, will it fit there? Hopefully. Okay, maybe I'll write down because it will be quite important. I will write down on this blackboard, separate, why not? And so here I will write down everything which is connected and which is the sort of the final things which we are looking for. So the main source of the convection stability, we mark him as like S prime, small s prime, and it has index 0. And this can be represented via the input heat flux minus output heat flux, which is given, of course. Then it has the adiabatic heat flux contribution, which work here on all the sphere. Again, RO. Then there is a difference. Actually, there is a volume of the spherical shell. Here we have a volume of the spherical shell. Cube, sorry, cube here. And it's multiplied by K T double prime, which is given. So this is the adiabatic part, and this is the given contribution. And then it's divided by, it just normalizes it actually, by this adiabatic flux with addition of the temperature for P, T, R, small k, And here we have, again, the similar adiabatic heat flux contribution. So there is one source. This is all constant are here. So this look like the radial distance. So this is the first. Actually, all these R dependence are coming from this Laplacian equation. The first solution of the Laplacian equation is dependence on R. And another solution of this Laplacian equation, maybe more precisely to say that it's Poisson equation, because there is constant here. So, and the second one is inverse power of spherical radius. So, and it's writing down like this, QE R cube. Oh, QO, sorry. Okay, we start here from QO R cube. Oh no, I wrote correctly, but sorry for my mistake. QI RO. Then we minus QO R I. There is some exchange between these two values. Cube. Then we have the similar denominator like this, but slightly different. It's 4p t rho k RO cube minus RI cube. And this is also acting like the, okay, let's write it in slightly different way than in that notation. Inverse R squared. So this is the major source of convective instability. Actually, it appears in the equation later. I will show you in comment. And there is also another source of convective instability. This is direct source of the buoyancy, which is due to the input and output heat flux. And there is some subtraction from this input and output heat flux, which actually there is adiabatic heat flux. So this is the major contribution, which is coming out due to some input or output heat flux. And it's also some advantage of this term is that we can not only thermal convection imitate with this stuff, but compositional convection also could be imitated by this stuff. Because if we suppose that this inner heat flux is positive and has some sufficient value, then it can imitate the compositional convection. While this output heat flux basically imitate the thermal convection contribution, and this thermal convection contribution could be even in opposed to the generation. But the one which is from the inner core and basically mainly due to the gravitational differentiation, it always has a positive contribution. And the similar play is for this another term, but maybe slightly different arrangement. And the second, also maybe not so also important contribution to the convective stability is actually connected with the time derivatives of the total entropy. This is related to the time derivatives of the total entropy, and it depends on the total heat flux, normalized heat flux, which is not this heat flux, but the similar heat flux, which is actually responsible for the radioactive cooling, for example. And it works like that. It has two terms. One is depend on the radiative cooling, and other is also connected with this input and output heat flux. And it basically, this stuff is working like the cooling down of the planet. Just cooling down of the planet due to the excess of the output heat flux. And here we have the similar denominator for P, T rho, Rho cubed minus Ri cubed. Okay. So it constitutes the formula which one here 412 and 413. Okay. So here we have some index O that denotes the stationary solution for the superadiabatic entropy. This index O, this one. And the prime denotes the direct derivative with respect to the spherical radius. We have some prime, maybe not so much of them. Here there is a prime. It denotes this value. Actually, it's enough. So it is obvious that the spherical layers with a negative source of convective instability S, when S prime is less than it is obvious that spherical layer with a negative source of convective instability SO prime less than 0, SO prime less than 0, promotes the development of the convection. So if S prime is smaller than 0, then it's promote convection. This one things. And in opposite case, if it's positive, of course it's acting against convection. And sometimes it happens, especially if this output heat flux is not so sufficiently large. Then, on the contrary, in the layers with a positive source, stabilizing occur. For example, it could be referenced on my paper. We especially emphasize that the convective source 412 does not include the internal heat source Q, which is estimated very inaccurately. This significantly simplifies the study of thermal convection in the deep interior of the planets and moons, since it's reduced it to manipulating more confidently estimated heat flow. No, here there is a reference on Braginsky, Roberts, Starchenko, and John's work. We use the simplification introduced at the beginning of this section and the obtained source of the convective instability to finally formulate the system of equation and boundary condition for nearly adiabatic convection in the form most convenient for further use. We transform the equation of motion 4.48, the law of conservation of mass 4.7b, and the law of conservation of energy 4.78 to homogeneous. So actually without direct sources, it's important that we finally have homogeneous equation in form. So let's write down the final equation. Here there is the equation for the source. Now let's write down the final equation itself. Okay, it's enough space here. Of course, first coming is Navier-Stokes equation. Not so much changes in it. Let's just put in one place everything what depends on V. Oh, okay. So then we are writing down the Coriolis term. This is based on the unit vector in the direction of the axis of rotation. And here there is vector product on V. Then there is modified pressure. And then we have contribution of the viscosity. And it's here there is a place where some change things are changed. We have here, instead of the coefficient which link it to the divergency condition, because we have not exactly divergency condition, we have the condition not divergency of V, but we have the condition divergency of rho times V. This is adiabatic. So this term, which is related to the divergency in this form, slightly transform it, and it takes the form 3 theta rho prime, which is given above, and rho squared, and gradient of the radial component of the velocity. So this is perhaps maybe I paid too much attention to it. Of course, in the Earth it's not so important, but it can be very important, for example, in such a planet like Uranus, Neptune, and especially Saturn and Jupiter. So, and the next term is not changed, it's just ordinary ordinary viscosity term. And of course, there is a buoyancy term which drives the buoyancy. O divided by Cp per O. And here we introduce, instead of the deviation from the convective velocity for the entropy, we have anything that is on top of that. You know that previously so actually our deviation from the adiabatic state has two components. One SO and other component, this theta. So we use this relation. Oh, sorry. We just use this theta, which is on top of the hydrostatic solution, which we previously obtained from this system. So it's on top, and this set like that. Okay, let's just stress it. And then there is a divergency condition. This divergency condition is taken into account divergency of the density. So divergency condition is not divergency condition complete, but also it includes dependence on the density. And it takes the form rho strich prime over rho and radial component. Of course, it's again have not so big contribution in the terrestrial planets, but it could be quite sufficient, and maybe even the major contribution in such a planet like the Jupiter and Saturn. And then we have perhaps the most important equation in all this system. This is the equation for the entropy, but not all entropy, but this entropy which is on top of the hydrostatic solution. And this is actually, it could be written like that, d theta by dt, substantial, very substantial derivatives. Then we have the ordinary term like k q theta. And the main things here which is appear and which is drive actually the convection and include all the input, output, and so on flow is namely this term which we specify here, and it's multiplied by the radial component of the velocity. So perhaps it's the main drive, I just stress it out. So eventually we have 414, and there is A, B, and C. I just substitute them via the comma. From here on, the effective pressure per unit of density from 4.48, this effective pressure, is now denoted by the letter P. We just to understand that this is actually effective pressure. But because it's only entering in one place, why not to have some extra addition to it? We just replace it by this P value for simplicity. So not to be confused with the expression, to know that this pressure not to be confused with superabatic pressure from the previous section 2 and 3. And the specific entropy, other words, we can reformulate this, that this specific entropy theta is equal as O minus S. It is the same stuff. Here and below represent not the entire, see above, terabatic entropy, but its dynamical part minus the stationary solution, which is necessary, is obtained from 4.12 and 4.3b, this one. This 3b, 4.12 is here. Okay. The chosen homogeneous form of the heat transfer equation 4.14, this equation, allow us to write the thermal boundary and normalization condition also in a simple homogeneous form. So actually, after substituting of all this stuff, we simplify somehow the boundary condition for this value, because it's on top of the hydrostatic equilibrium, and simplify the equation. So of course we have the normal boundary condition for the velocity. I will not list them here because everybody knows, but we should specify the boundary condition for the entropy. So finally we have d theta, more precisely of course not entropy, but the entropy part which is on top of this hydrostatic part and on top of adiabatic as well. So it's just some additional stuff, and it's d theta by dr. Actually we can put it in 1 at r equal ri and at r equal RO. All of them are equal not. So there is two conditions here. And there is one integral condition which slightly changes here because it takes form of the integral over all in a sphere, over all rotating liquid sphere. No, sorry, liquid spherical shell. Yeah, of course, liquid spherical shell. Ri and Ro. And this integral is acting on 1 minus rho prime, which is constant in our condition, over rho also constant in our condition. And here we have R. You can see that the dimensions are satisfied. So then, and it's this integrate over the theta, over theta on the volume. So this is boundary condition constitute formula for 15 A, B, C, 3 formula. And more precisely, this is not boundary condition, but integral condition, global condition is possible to say. And these two boundary conditions, just homogeneous and simple condition. And we need that because we put this condition on derivatives, so we have it's necessary to have extra condition to determine the complex function. The final almost adiabatic system of convection equation, which is written on this blackboard completely, is closed by the boundary condition on velocity, which I, as already told, is quite obvious. I will not write down them. And for example, for terrestrial planet, it can be written in the form of no slip condition. This is no slip condition means that it's all the other what it means that directly on the boundary we have zero velocity in the system of coordinates which rotated together with this boundary. So this is other representation of no slip condition. Okay. It seems I finished this part. So maybe there is some question. Yeah, please. 4.12, yeah. S null must be greater. No, to promote the convection, it should be less than 0. Yeah, to promote the convection, it should be less than 0. Here, if it's greater than 0, then it's suppressed convection. So making some things more stable.
Sir, 4.14b, that 4.14b, the continuity
This
equation.
one, yeah?
Can you comment on that once?
This 414b, originally it looked like that. We have this is equal not. If we expand this row,
yes,
over the constant term and the term which variate so we have gradient of rho, say rho O component plus rho prime R. This is also constant, rho prime, and this is constant, it's some average. Then, okay, better here. Another bracket. if we open all the brackets and act operator enable only by R,
Okay.
because only R is acting here, so we get this
Okay. Okay.
this one.
Okay, sir.
Okay, one more question.
Sir, previously in the basic equation of planetary convection, we neglected that term, that zeta. In the gradient of, in the momentum equation, right hand side first term. So in this slide only, no, previous. Equation 4.14. Yeah, we were neglected the right hand side of first term. In the basic equations of planetary convection. No, sir, the first equation.
First, now yes.
Yeah, Navier-Stokes equation.
Yeah, what do you want to neglect?
Yeah, previously we have neglected, you have told us that the divergence of del dot V equal to 0. But here we have taken the divergence of del dot V equal to that constant of...
Which divergence? I don't understand.
Yeah, that's right.
Please
Okay.
say,
What
say,
about
please
here?
say this divergence.
Yeah.
So you're speaking about this term. Okay, this is
Okay, but
actually in our previous consideration we neglect this term in the earth.
yeah.
But here I return this term just because I am trying to write down more general equation than we previously considered. So the maximum possible general equation. So now we actually, when we return this term, you should consider not only terrestrial planets, but also the planets like Jupiter, Saturn, and for example, icy Gian like the Neptune, and so it's just more, and it's not required too much effort to include this term. So actually, it's just the thing which, but of course, in terrestrial planet this is small, because here the variation of the density is just 10%. So it's normally at least 10 times lower than this one. But in fact, even more, because effectively we have here just gradient of the R, and here we have double derivatives. So if we divide it on the small value, then we even raise the ratio. Of course, in terrestrial planet, but in the such a planet like a Jupiter, where density change more dramatically, this term is working. Something like that.
So especially for Jupiter, Neptune and Uranus, these kind of terrestrial planets only we will consider.
Exactly, yeah.
Okay. Thank you.
Okay, let's have a break. Or maybe somebody will ask more. Understand on all the basic things. I tried to deliver these basic things to you in every detail. Maybe I'm wrong in this way, because only 2 days of the course remains, less than 2 days, 1 day and 2/3. So actually, in terms of the lecture hours, so actually maybe I'm just suggesting that I will very briefly introduce you the topic which are sort of the general topic, and then we proceed to the case maybe on the next lecture, or maybe in tomorrow, but perhaps I hope now on the next lecture today. We proceed to the critical convection itself in a asymptotical point of view in this wonderful solution. We just, of course, it's impossible to deliver to you every detail of all this stuff, because it's vast. So we need to. Let's first stand for the next lecture, which is about kinetic and total energies. And this equation, which is shown here, could be obtained from the Navier-Stokes equation if we just multiply the Navier-Stokes equation by the velocity. So this equation, which is on the display, could be obtained if we just multiply by velocity vector. This is a scalar product. We take the scalar product of the velocity vector on the Navier-Stokes equation, or more precise, or other words to say, momentum equation. And you see that here, on this notation, you see the first things which is appear here is the derivatives of the v square divided by 2. This term is appear from the this scalar product, which we multiply on the dv by dt, partial derivatives of v over t. And so when we scalarly multiply it, we get this obvious result that we have taken into account as well that this adiabatic condition rho a times v vector is divergence free. So we get such a simple stuff. One could ask, where is the v grad v term? It's actually disappeared. It's the advantage of this representation when you multiply by the vector velocity in scalar way. So this complicated nonlinearity is completely absent. And the nonlinearity becomes, because maybe you remember that actually this v grad v is better represented via the v times in vector sense on the rotor v, and here if we multiply by velocity, then this term is cancelled out. Another good news that the Coriolis force is also cancelled out from this relation. You see there is no Coriolis force. And here this is direct consequences that we multiply the vector of velocity on the scalarly, we multiply on the vector product of the in the direction of the unit vector in the direction of the axis of rotation and velocity itself. So we have again 0 when we multiply scalarly all this stuff. So we get rid from the most difficult terms. And so then the energy balance, kinetic energy balance, of course, this kinetic energy balance is reading quite simply. You see that it's include diffusional term in such a way, and this is only nonlinear term which appear here, and it's much more easy to treat it. And there is a buoyancy Coriolis term which is here, and there is some remains which we can put in the divergent form. And they are actually on one boundary, working on one boundary, and another on another boundary. If we want to consider the integral of all this energy, these things which I showed previously was only for the case when we have integral, when we have local balance of the energy contribution. But if we integrate, we will get further simplification. We obtain that the total kinematic, I'm sorry, where is the mouse? We see that this total kinematic energy, this one, in terms of the X and everything. So this total kinematic energy has a following contribution. First, usually positive contribution is coming from the buoyancy force. You see it is here. And actually all the convection is related on this buoyancy force, where A is the buoyancy acceleration. In our previous formula, which we showed to you, we see that this buoyancy acceleration is due to the variation of the entropy over the adiabatic state and over hydrostatic state. And so it's this buoyancy acceleration is working that it's directly proportional to this component of the entropy. And here there is a contribution from the different terms of the viscosity, and they are also quite simple. And also there are some contribution directly on the boundary, because we have this simple explanation that we have evolution of the kinetic energy due to the, first of all, by due to the Archimedean buoyancy term. Then differential rotation, and this is the nature. But nevertheless, all this term, viscosity term, especially this one on the boundary, could be neglected, and the major balance, again, just to state you to understand how it works, and the major balance is between the Archimedean buoyancy force and the viscosity. So the next, let's take, so here it's written how this viscosity works, and the normalized heat flux from the viscosity can be represented like that. It's exactly taken from here. So actually it's work like that. And also we can take into the consideration not only kinetic energy, but internal energy as well, which is denoted here by epsilon. And here there is we have again the similar balance, and in this case we should include in the balance the radioactivity heat source, which is usually, for example, in the planet it could be quite valuable. And this balance in the differential form look like that. And if we proceed further, we can replace the terms from here by the entropy terms, including this entropy terms, which is responsible for the cooling down of the planet. We consider the planet we are discussing. So, this is the end actually about the kinetic energy. Okay, kinetic and potential energy. Is there any questions? I'm just trying to make it more faster without writing on the board. But later, when I will proceed to the crucial, to the excitation of the velocity field and convection, then of course I will be in more detail, because the critical convection is one of the most important subjects which we should describe in some detail. But maybe there is some question about kinetic and total energy and other energies. If there is no question, let's proceed to another topic. Okay, we remove that. And then we proceed. We proceed to the chapter which named cooled temperature and pressure be basic thermodynamic variables. And again, in short terms, we considering the temperature T and pressure P in the main thermodynamic variable in the equation of nearly adiabatic state, which could be referenced as 4.1. Instead of superadiabatic entropy, we should use the superadiabatic temperature. As a result, instead of for 1 we obtain. So the result diabatic entropy, the same for the gravity potential, and I just told you this variation in the temperature. And then in this case, entropy is not main plane term, and we should separate it out, and to present via this pressure and this super adiabatic temperature. So let's consider how this works in more detail. First of all, we could consider the hydrostatic equilibrium, like it's written here. Then we expand in thermodynamic variables, which are now we're trying to prove that we could use the equation with the temperature and pressure as basic thermodynamic variables. And eventually we have this representation via the modified pressure, which in fact not pressure, but the pressure divided by the density, and there is the inclusion of the superadiabatic gravitational potential, and so on. Also, there is a pressure here. So, of course, we put this everything to the Navier-Stokes equation, and Navier-Stokes equation changed not so much. It's also very similar to the equation we have. And also there is this form of the gravitational potential. And then we should jump to the equation for the the problem is that we first of all, if we suppose that the pressure and temperature is the basic thermodynamic variables, then in the equation for the entropy, we have them both here. You see that the instead of the simple equation for the entropy, instead of the simple equation two value of entropy of the pressure and the temperature, if we separate these two values on two independent equations, so we have addition. We have extra addition if we before that we use only one equation for the entropy. In this case, when we name the pressure and temperature as the basic thermodynamic variable, we instead of the one equation actually for the energy, or more precisely for the entropy, we have to use two equations, one for the superadiabatic temperature and one for superadiabatic pressure. So the order of the equation rises very sufficiently. If it was equation of the second order, so now it becomes equation of the fourth order. And everything is in partial derivatives. Of course, it's much more difficult to solve this problem either numerically or either asymptotically or in any case. So maybe this is, in very short terms, is the proof that we cannot use temperature and pressure as basic thermodynamic variables. And why this question occurs and why this question arises? Because the majority of the work which is devoted to the planetary dynamo and especially to the some planets where of course the major amount of all the work which are very known in the world, that they almost all of them are having deal with pressure and temperature. They are not prefer to handle with the entropy. But then they use, in fact, they use the deviation of the temperature, but they are not completely true. They are not completely doing right things, just because they are taking into consideration only one equation, this equation of the temperature. They are not taking into consideration equation for the pressure, which should be appear in this case. And we could give rid of the equation of the pressure in this case, which is written perhaps here. Oh, no, we wrote it in our previous work. Something based on this presentation. And actually, in terms of the pressure and temperature, we have almost equal contribution from the pressure and from the temperature to the entropy. But in terms of the entropy and pressure, we could neglect the pressure contribution. And we simplify the system very sufficiently, and namely this system is working. And why some people who are doing this stuff still have some success? Just because the entropy equation is quite similar to the thermal equation. But they didn't recognize that they in fact working in the entropy field, not in temperature. So this is just to show, and also of course we can take into consideration the boundary condition here. But the main thing of all this stuff is that if we want to use the pressure and temperature as the basic thermodynamic variables, we finished up instead of the second order partial differential equation for the energy, which is in fact entropy equation. We should solve an extra equation. And this it's also pays the problem that because not only this extra expression, you see that this pressure is entered here. And it also involves the gravitational potential. So our problem rises tremendously if we use the pressure and temperature as the basic thermodynamic variable. So this is sort of all the people to understand how they are working and work in the entropy field if they want to get the right result, and most important with not so much effort as it's required. Okay, so I finished actually very briefly this next paragraph, next chapter even next chapter, or maybe more precisely to say paragraph, because chapter is in more. And so if maybe there is some question about this chapter. Small c square, which in square? This is the speed of sound. Speed of sound, yeah. Okay. And maybe more questions? Okay. Okay, please. Sorry?
This means pressure and temperature can be used as thermodynamic variables.
Sorry?
Pressure and temperature can be used as thermodynamic variables.
In equilibrium?
No, pressure separately or temperature separately as thermodynamic variables can be used.
I don't understand, sorry.
So basically I'm asking the topic only, that temperature and pressure can be used as variables of thermodynamics.
No. The main conclusion of all this topic that it's better not to use pressure and temperature as the basic thermodynamic variables because it leads to a lot of difficulties. And in fact, it's much more better to use the entropy and pressure. And when you use an entropy and pressure, all the most important terms of this equation, especially first of all the buoyancy term, then we can neglect the pressure contribution. And if we neglect the pressure contribution, the system is dramatically simplified, and actually it's working much more better in numerical sense, asymptotic sense, in any sense. So this is just a proof that it's wrong way to use the pressure. Yeah, exactly. So. Okay, so did we finish with that stuff? Okay, if we finish with that, let's stop for the moment. Let's see where we are. So we actually very briefly proceed on 2 paragraphs. And the next paragraph which we have, this Maria give you tasks, so maybe we will not discuss them here. Maria, you're actually in our list of the lecture. There is the exercises for the chapter 4 here. And did you finish this already? We discussed it again. Okay, so I proceed further. I'll proceed further. Oh, okay, bingo. We on the critical convection now. This is chapter 5. Okay, let's see. Where is it? Okay, we are here. Okay, let's proceed further. I'm missing time a little bit. How many time we spent already? 30 minutes? Something like 30 minutes, yeah? Okay. Okay, so just in 30 minutes we passed 2 chapters. So now proceed to the critical convection. Okay. This is the actually section chapter 5. Oh, no, it's writing badly. Okay, we proceed to chapter 5. It's named critical convection. Okay, maybe it's rather important stuff which we now in. And this section 5 is to determine the condition for marginal stability of convection in the liquid core of the Earth type terrestrial planets or moon. These objects are all in the state of rapid rotation, for which the viscous force, as measured by Ekman number E, is many order of magnitude smaller than Coriolis force. Actually, we already stressed on this point that the Ekman number is actually acting like the effective viscosity, sorry. So this is viscosity is 10 to minus 15 for molecular value, and for turbulent value it's roughly 10 to minus 8. So anyhow, it's quite small, and it is many order of magnitude smaller than Coriolis force. Since realistic Ekman number are extremely small, we use asymptotic method based on small Ekman number. In this way, we find new results using the standard local asymptotic method introduced by Roberts in 1963 and Bussier 1970. So founder of all this asymptotic critical convection approach was first Roberts, in 1968, and the second is Bussier. And Bussier in 1970. It's based on turbulent transport coefficient, and we calculate the critical parameter of the marginal stability of the convection. Here I just describe the essence of this chapter. And then let's start this chapter from the linear asymptotic system. And the original system of convective equation includes the continuity equation, which we already saw in many occasions, the equation on heat transfer or entropy equation, the Navier-Stokes equations of momentum equation, the equation for the gravity potential, and the equation of states. I will not repeat them here because we already saw them a lot. I just remind you that perhaps the first defined all this set of the equation was Greenspan in 1968, then Landau-Lifshitz in 1988, then Roberts and Braginsky together in 1995. And to obtain the unique solution, the convective system must be solved subject to the corresponding boundary and other necessary conditions. And the using classical Boussinesq approach, actually all these persons were using classical Boussinesq approach. And this, as already told you, Boussinesq found this approach in 1871. Then before him was Oberbeck, and also Boussinesq make 1903 the work. But here there is some important correction that Boussinesq actually, everybody regards that he created his work in 1903, but there is one work in 1871 which Boussinesq did. But it's maybe not precisely the Boussinesq about Boussinesq convection, but nevertheless it gives a priority on the Oberbeck, and so it could be fixed and known. And which is probably the simplest and most widely used the initial system can be, and it can be significantly simplified. Actually, the first assumption generally employed in the classic Boussinesq approximation is that of very small relative density variation. And it allows one to use the simplified continuity equation. The simplified continuity equation we use, first of all, that instead of all the substantial derivatives, we suppose to put the zero, totally neglecting of the sound effect and sound wave. And it's just simply divergence of V equal naught. And this constitutes the first equation in this chapter. This is, of course, a very simple condition, but nevertheless, it's allowed to reach some results. And the second Boussinesq assumption can be expressed in the form of the requirement that the heat of energy variations are mainly due to the temperature variation. As already in my previous talk, I just told you that it's maybe not right way, but in the case when we have could suppose that the divergence is actually not, of course there is some deviation from the divergence just to have variation in the density for convection to rise and to work on. And so this is, but this taken into consideration in Boussinesq approximation only when on this boundary term. So here there is some simplification, but nevertheless it's work. So this means that the heat transfer is described by the well-known Fourier-Semel equation of heat conduction, which provides the second equation of the Boussinesq system. The first equation is the divergence-free equation. Then the second is the equation for the temperature. Here there is known constant. There is substantial derivative of the temperature over dt. And also there is Laplacian term, which effectively applies the divergence of the following gradient. Kinematic diffusivity K, then grad T. All of this is actually diffusivity contribution. This is Euler type substantial derivatives contribution, and also quite possible that there is an internal heat sources, and they can be written in such a form. And just let me stress that it's not heat flux directly, but heat flux per meter square per area. Perhaps the most, okay, let's number it. Perhaps the most important and difficult equation to solve in the original system of planetary convection system is Navier-Stokes equation of motion. So you can see this equation in the various publications, including our consideration. So I will not repeat its general form. I just repeated form for this Boussinesq approximation, with of course some simplification, but rather sufficient to our first goal. And here we can write the third equation, which is Navier-Stokes equation. In this case, it looks like, okay, I should move. Okay, I just show you equation. And here, perhaps also important things happens, that to write down this equation like it was written here, it's necessary to suppose the following condition for the thermal expansion coefficient. And then we have this second equation, or third equation, sorry. Equation which is in fact Navier-Stokes equation. There is a Coriolis term, of course. There is the unit vector in the direction of rotation, and it's multiplied by the cross vector product on the, oh, sorry, what I love. I wrote the magnetic field. Sorry. Of course, velocity. Okay. And then there is such a term like a grad P, capital P. It's important to note that it's capital P on rho. Rho we regard as a constant. This is the density. And also we neglect all the component of velocity which are not working in this approximation. We leave only Laplacian one. This is kinematic viscosity nu, and there is Laplacian of V. Okay, and the remaining term is the gravity potential. So it's 5.3. Okay. Here we consider fluid of uniform constant viscosity nu, which rotate with the constant rapid planetary angular velocity omega about the constant unit vector 1z, fixed in space. Then centrifugal acceleration in 5.3, in this formula 5.3. Oh, let me proceed. Oh. Okay. 5.3. The centrifugal acceleration in 5.3. I hope to miss this glasses. Oh, sorry. Okay, the centrifugal acceleration in 5.3 is neglected with the accuracy of order 0.5%. So we just even don't write it down, but it in the comparison to the standard gravity acceleration. So we use the standard gravity acceleration, which is actually this grad U. So in other words, this is gravity acceleration, which usually denote as G. Gravity. And it's much more than centrifugal. So we neglect centrifugal. Okay. And the final Newton self-gravity planetary equation is actually nabla square U is equal 4p gravitational constant and rho. Of course, it's the same equation which we consider with U, but only in some simplified form. And the temperature profile in our spherical geometry can be presented in the form. We present the spherical profile. Like steady temperature profile. Okay. There is a steady part which depends only on radius. And there is unsteady part which we denote here like tau, and it's actually depends on all coordinates. Let's put all coordinates like the r vector, and of course it depends on time. So it's actually the value we are looking for and examine. And here tau s is the steady temperature profile, and tau which depends on all coordinates and time. This not depend only on the radial coordinate. Steady temperature, and actually this tau is convective part, which is cause the convection and support convection and so on. So to be consistent with previous studies of the linear stability of thermal convection in a rotating and spherical shell, reference there, we take the outer radius of the layer RO as unit of length. So here in this approximation we will follow the initial contribution which was made for this person, and they usually used even not spherical shell. They started with using the complete sphere. So in this condition, it's not convenient to use the radius of the inner core, but it's more convenient to use the radius of the outer core. And in some cases, it's even the radius of the sphere. If we consider the sphere, of course, the first case which all people consider is just sphere. We fill it completely by the liquid, and there is a constant heating inside it, like the radiation heating and so on. So we take the outer radius of the layer unit of length, then the viscosity. So unit of length, as we discussed that it's not good to make R, let it be L units. It's of course the radius with mark as bad star, units of length from the both length. So it's the units of length. It's the ratio of the sphere. We will not specify outer sphere, any sphere, at least some sphere which is on top. Okay. So then we use the viscous time. Viscous time is quite naturally appear as a typical time. So typical time T with star is equal. If you consider the dimension of the viscosity, you see that it's actually meter square per second. So to construct from this value the characteristic time, it is working like using again characteristic length. So it will be RO squared over the viscosity. So we use this like the characteristic time. And the effective pressure, quite useful in this respect to measure. So we have the effective pressure value. I just remind you that the effective pressure is not just pressure, but the pressure divided by the density. this density is constant here, and it simply scale it out of the system. So the pressure will be have the natural units of 2 omega nu. We use this representation because the pressure, first of all, compensates Coriolis force, this Coriolis force. So we use it as a unit. And then, using these units of measurement together with the above parameter, we obtain in dimensionless linearized system of Boussinesq equation. Okay, will it fit here? Okay, I'll try to fit it here, but I'm not sure that I will fit. Okay, let's try. Okay, first equation is, maybe. Okay, here is a non-dimensional equation. Let's write them down and comment. First one is, of course, divergency precondition. And we number it at 5.48. Then the next in importance is the Navier-Stokes equation itself. So, and it has very interesting form. There is Ekman number, which you know, I will not define it here. You know the Ekman number, so I just wrote it in the right place. And there is a substantial derivatives of the velocity. There is, of course, Coriolis term. And because we scale it out omega from here, this equation, so it has a rather simple form. And of course there is a pressure, again modified pressure, actually pressure divided by the density. And all that is equal, again, Ekman number. Then Rayleigh number appear. I will describe it later. And in front of the Rayleigh number, we have this tau, which drives the convection. And there is simply vector of the radial spherical vector. And the final term, but perhaps the most important one, because it's actually produce the influence of the boundary condition of the flow, is the viscosity term, which in this non-dimensional units becomes like that. Five, 4b. Okay, you see that even at the first glance, you see that you give rid actually of this term. And this is a very good thing, but nevertheless, it's, you should be a bit careful, because sometimes there is some derivatives here. And there is some time where we cannot completely neglect that stuff. We should take into consideration some short times, and some derivatives will appear here, especially we consider. But at the, if you like, 0 or maybe first approximation, we can just disregard this term. If we disregard this as well, then we have a geostrophic flow, actually, type of the geostrophic flow, which could be also estimated. But to solve the problem completely, we should keep that. Best of all, of course, to keep all the terms, except maybe this one, because especially in this, its nonlinear part, it's not so important. Okay, so let's proceed the final equation. So the third equation in this system is the temperature equation. It includes Prandtl number. Then it include this instability contribution, which is very similar to the contribution we discussed previously. So this is instability contribution, which is due to the gradient of the imposed temperature. So we have usual condition to model this value, this thing is to have one temperature on one boundary, another temperature on another boundary. So there is a gradient of temperature. And it has some hydrostatic part. And this hydrostatic part is actually the main driver of the convection, which manifests the convection instability. And this gradient T is simply multiplied on V. And since this gradient, as already showed you in my previous presentation, is basically on R, so all this combination finally means that here we have derivatives and here we have just R component, because this depends only on R. Let's just split. Just to understand that actually, namely radial component of the velocity produce the convection here. So, and also, of course, there is the diffusion term, which has very simple representation here. It just nabla square on tau, or as was lambda tau. Okay, let's A, B, C, 5, 4, 6. Okay, let's just, okay, I will not write down the Ekman number, you know it very well. The only difference in this Ekman number and the one we used before, maybe you see that there is no 2 here. So actually we use this 2 in the Ekman number, in determining the Ekman number. So maybe it's worth to write down this everything. First of all, we write down Prandtl number. Prandtl number is, okay, are they listed here, not? Ah, yeah, everything is listed. Prandtl number is ratio of viscosity to diffusivity. Then Rayleigh number is the ratio of all the terms those are responsible for generation. This is alpha expansion coefficient. So it's show how much is the expansion with the change of the temperature. If temperature rise, so in corresponding relation, this alpha coefficient give. Okay, maybe I was a bit in a hurry. So the next Rayleigh number, which is equal alpha Ts prime, actually derivatives of this state. Then there is gravitational acceleration on the outer boundary, and there is the radius of the outer boundary. So actually all this stuff is quite sensitive to the size, because you see that here it's entered in 5 power. So this is the reason why this Rayleigh number sometimes could be very big. For example, on the Sun it could go up to 10 to 30. And the Earth it will go up to 10 to 20, 25 or something like that. So, and on the bottom, we have all the effects which are against generation of convection. So this is in favor of the convection. And also there is one thing, that this gradient, actually there is a prime mean derivatives, it's negative, as we already told you. So just to have the positive value, we put here minus as well. And here on the bottom we have all the terms which work against the convection. It's of course viscosity and diffusivity. And the Ekman number here, which appear here, is slightly different, and this difference is quite obvious. We just include 2 in this. Not we, but Roberts and Busset. Okay, so they started this stuff. Two is here. Okay. So I just remind you that the alpha here is the coefficient of thermal expansion. Mu is the kinematic viscosity, K is the thermal diffusivity, and G0 is the gravitational acceleration, and exactly at the outer boundary or the radius of the outer sphere. When the fluid is at rest, the steady temperature profile Ts of air from air and its derivatives depend on the heating mode that is constructed. Most of the known works consider either so-called internal heating or differential heating. In the first case, it is assumed that the distribution of the heat sources is uniform in the fluid volume. In the second, that the temperature values are fixed at the inner and outer boundaries of the spherical layer. And let's follow the work of Domi and others, and we write this profile in this form. Actually, this profile determines all the, okay, I started perhaps from this point to state the system. And to complete the statement of the system, we should show the profile, this TS profile, which actually drives the convection. And in case of the internal heating, this profile works like that. Ts is equal minus 1/2 beta r square plus TO. TO is the value on the boundary, value of the temperature on the boundary. And actually for us not TS is important, but important is the gradient. And the gradient actually is equal, because gradient is entered here. This gradient is equal, as you easily could see, minus okay, I remove the Ekman number because you know it, so I remove it. Just to give a space for that. So it's equal beta r and the unit vector in radial direction. It's constitute formula 5A. So this is the internal heating, and also we could have the differential heating. This actually works when we have some value which is distributed uniformly of the heat flux inside the sphere or spherical shell or whatever. But it's possible to have the differential heating when we have one temperature on one boundary and another temperature on another boundary. In this case, there is a slightly different to differential, of course again heating, the same Ts, the similar Ts is T1 over R plus T2, and the gradient is again negative, minus T1 R squared R. Oh no, not R. Unit vector in R direction. This is differential heating. Okay, I succeed to fit everything. And here T0, T1, and T2 are the constant determined by the boundary condition. Actually, it's not exactly the temperature corresponding, but it's some constant which we can find in the within the boundary condition. So, okay, it speaks, since I spoke even slightly more than 1 hour, so we can finish this part. And of course, I'm waiting for your questions. Okay, please.
Ts prime is basically the differential coefficient of Ts with respect to R.
No, it's Ts is the given profile of the temperature field. It's just given profile of the temperature field. And this profile is usually if we have internal heat sources which are distributed with uniformly distributed in the scale of spherical shell. So it has this temperature profile is look like that. So its gradient is actually just proportional to the R. But in the case when we have differential heating, because as you are asking, we put one boundary at one temperature and another at another temperature. Usually, for the case for the Earth, we have inner boundaries at higher temperature and outer boundary at lower temperature. So the effect is that it's heated from below, and is correspondingly it's cooling down from above to support to maintain the fixed temperature. And this is so-called differential heating. And this differential heating works like that. The profile is in inverse R plus some constant, and the gradient is just inverse R square.
So what is Ts prime? Ts prime in the Rayleigh number
Ts
equation?
prime is the gradient actually.
Okay.
This gradient, so Ts is dependent, Ts without prime is dependent on radius.
Okay.
And the prime means that just derivatives in the radius.
So it's basically the gradient evaluated at what point of R?
It's some average.
R not. Okay. I mean R's a typical
Yeah,
value.
because when we determine this Rayleigh number, usually we speak about some average values.
Okay. Thank you.
Okay, one more question. Actually, negative signs means that the temperature is rising with the depth. So in case of the Earth, the more deeper we are, the higher the temperature. So it's in inverse order that if air rises, then this gradient will be positive for air. But in contradiction, the temperature is declining with the growing of radius. You grow radius, and growing with radius, the temperature is declining. So it's actually resulting in that minus in the gradient. So we just of course we could consider with this prime some, I don't know, average or modulate stuff, but we just using sort of the original approach, so they use it like that, so we just follow. Okay, yeah, exactly. Yes. Thank you. To make things a bit clear. Thank you. Okay. It seems we spent more than 1 hour, so perhaps we have to have some small break. Or maybe big, I don't know what Rani said. Maybe just small. Maybe just small to finish up. Small break. Yeah, small break. Yeah. One more. Okay, please. Maybe.
You can put there.
Okay. Okay, let's go further. Please put record. Okay, in what following, we just formulate the system itself and outline it all the most important parameter in this system. So now let's proceed to the local asymptotic solution. As I already mentioned to you that we have local asymptotic solution, first of all, which was found by Roberts and Bousset. It has very local nature, but has very famous history. And then in this history, this local asymptotic solution was and Roberts. And of course it was other researchers not so well known. So the first solution for the problem of convection in a rotating spherical shell in the limit of small Ekman number and with internal heating was found by Roberts in 1968 using WV-KB approximation. So Bousset used WV-KB approximation. And Bousset, in 2 years, studied the onset of convective instabilities of a cell gravitation internal heated rotating fluid sphere. The results of the perturbation theory for this problem showed to be in agreement well with the results of the extension of the analysis by Roberts. Before that, 2 years before Bousset, it was analysis by Roberts, but Bousset actually introduced all this equation, which we already discussed it with you, but and nevertheless he used it like that. So then the constraining effect of the change in depth in the direction of the axis of rotation, as well as the gravity force and the basic temperature gradient, depend on the onset of the convection, and was obtained by the Bousset in the form of so-called very well-known cartridge bell of rolls, like that. And it was also experimental to the axis of rotation, like this. Oh, there is no picture. Ah, this picture, sorry, I found it later, but nevertheless, this picture actually. First I show you experimental picture of this stuff, but also there is the picture which is going from the asymptotic, and you very, very thin in this direction, which is azimuthal direction in the, on the cylindrical coordinate from the axis of rotation. And it's a very prolonged estimation, and also was experiment, but maybe we'll discuss it later. So the basis of Robert Bousset local theory is the assumption that the onset of convection is in the neighboring of critical cylinder. So there is some critical cylinder. Critical cylinder S equal S T, critical, S critical. Equation 5.4, which we got before that. Okay, actually the same equation can be linearized near the onset given. So actually we linearize the equation And this linearization results in this following system. We already show you our equation, but here to consider the onset of the convection, we should linearize this system, and this is quite simple trick to linearize this system. You can do it by yourself, but nevertheless the final result I will write down under some simplifications. So it looks like that. Of course, the divergence is free, first of all. Then we have Navier-Stokes equation. It's important to mention that if we linearize the system, we get rid of v grad v term. Here we have only partial derivatives in time from substantial derivatives. So this is maybe greatest simplification. And here we have plus Coriolis force in non-dimensional form. Then we have gradient P. And of course we have this stuff which is related to the buoyancy term, Ekman number, Rayleigh number, this tau which work on the convection, and spherical radius. And final is effect of the viscosity. Okay, this is 5, 6a, b. And then we have equation, heat equation or temperature equation, which include Prandtl number d tau by dt. Again, we give rid from the nonlinear term of the substantial derivative. This is the second place where we use this advantage. And so it's actually equal h. Boussais used not Ts like we used, but he used this h straightly for the gradient of the corresponding velocity. No, not velocity. The gradient of the corresponding temperature which derives the convection. So he straightly used the value which is, like h, and it depends only on spherical radius. And here we have multiplication of the vector v by the vector r, scalar multiplication, and it's obviously that this is r component of v times the spherical radius r. And then, of course, there is the diffusion term, which would be written like that. And this constitute equation 5, 6c. Okay, so actually we can specify here, directly here, that if we have internal heating, then this h is just 1. It's internal heating. And in the case when this h is equal one over r cube, this is case of the differential heating. So just see that if you here we have additional r, So in fact, when we apply this stuff here, we have 1 over r. We just have r. And when we apply this here, it's 1 over r squared. Effectively, because we have on top here r. So to begin the small Ekman number asymptotic analysis, we said it's important to use exactly to solve the divergence-free condition. And this is the simplest way is to use the stream functions. And this stream function in this geometry which we used here is actually based on the cylindrical coordinates. And more precisely, even not cylindrical coordinate, but on the axis of rotation, because axis of rotation and rotational effects are dominated here, and actually they contrast everything. So to begin with the small Ekman number asymptotic analysis, we said the following, that V is just equal rotor C and unit vector in z direction, and we defined one component, if you like, toroidal component of the velocity in this way, and a similar way we define the poloidal component, which contains double rotor. There is rotor of the next rotor of Xi to make it more pretty. Let's blow like that. Rotor. Sorry. Again in that direction, and we multiply by that. Oh, maybe better to put that way. We are taking the rotor. Okay. I was done mistake. I put extra. Yeah, more convenient to write like that. This is the rotor from rotor, and here there is C function, and in direction, unit direction of z, and here there is, we close the brackets. So this constitutes formula PF7. In this standard toroidal poloidal representation, it's actually toroidal part and poloidal part. You see that everywhere we have rotor. So this selection of the velocity field automatically satisfies to the divergence condition. So we could give rid at least with one equation. So the one equation becomes less. And also we have another advantage of this approach, that instead of the 3 components of the velocity, we have just 2 components for the stream function. Here exactly for the stream function, and this is some analog which go in the poloidal component. So this is toroidal component, and this is poloidal. And it's quite standard notation. And this standard toroidal poloidal representation, the velocity field satisfies the solenoidal condition, as I already told, and the corresponding vertical velocity and horizontal Laplacian operator are defined as, it's important to stress that this, in the case if we consider the, first of all, the Coriolis part, if we consider the Coriolis part of the velocity, which is of course rather important, And it's just very simply could be obtained here via the, sorry. Okay, so we just notate it like we define this value, which is the scalar product of the velocity and the unit vector in direction of the z. We define this value because it's quite important value. Actually, it's the component which is constitutes the velocity component in the direction of rotation. And later you see that it's indeed very important stuff. And in terms of all these things, it also has very simple representation via the modified nabla square of xc, and his constitute formula 5,8. And also we can define this operator, this modified operator, which is in actually working in yes. And here S d by ds and then there is azimuthal contribution 1 c, oh sorry, s 1 over s square d double on d phi squared, and this 5/9. Okay, you see that there is actually the fraction of the major fraction, maybe 2/3 of the ordinary Laplacian, of course square is here, of the ordinary Laplacian, but there is no z contribution here. So this is the difference. So it's make like the h, so mean horizontal. So it's sort of the horizontal in horizontal plane, not in the direction of rotation. So following Jones et al., Jones actually, Seward and Musa, we insert 5,7. Okay. Okay, we already passed that. So now we so we use 5,6b and insert all this representation to this equation. So eventually we obtain rather complicated system, which is working like that. Okay, I have to remove. Okay, that's, I don't know, is it enough space here? No. I don't know. Oh, maybe I'll better remove. Okay, just to simplify the things, let me not to rewrite all this equation. Moreover, it's already completely written here on the screen. I will just comment on the screen. I will not write down again this equation. It's quite lengthy. So perhaps I'll better comment on the screen. Okay, the first equation. Okay, I will comment with the mouse. Maybe it's easier. Okay. Here you see on the screen the first equation which we obtained by substituting the previous representation via the stream function and all corresponding function. Of course, we put it in the Navier-Stokes equation. And first of all, we see z component of this equation. It's the most simple one because there is no Coriolis force here. There is only contribution from the divergence on the time partial derivatives. Also, there is some things which is going after the value after viscosity. Oh, okay, I was wrong. There is Coriolis. No, it's not Coriolis contribution. Actually, it's coming from the pressure. And also there is some stuff which is also related the buoyancy contribution. It's here. And there is another component. Actually, there are only two components. And there is another component of this Navier-Stokes equation, which is written down here. It's a bit more complicated, but nevertheless, it's include everything, including Coriolis contribution here, and everything. And also there is the form of the temperature equation, which takes the form. And here there is the main driving term, which is here. It's appear here. And also there is a form of this complete. So I will not repeat it on the blackboard. I think that you can write down, if you like, directly from this notation. Okay. So the Roberts-Bousset localized asymptotic theory consider elongated structures of small horizontal scale such that, so they consider the following. This is now important thing. Okay. So first of all, they consider to have the all the structure in balance. They consider the derivatives of the in the azimuthal direction. They consider derivatives in the azimuthal direction, and they suppose that they are of order derivatives in the cylindrical direction, in direction of the cylinder. And to balance all this term in this equation, you can just check it, but it was checked by many persons, and you also could proceed with this checking. And then important balance is that all this d phi part, ds part, they are all acting like e to the minus 1/3. So each variable, each coordinate, we take the small variation of the coordinate here. So in fact, it's proportional e to the 1/3. And in the cylindrical radius, again, the same proportionality is working. So in some sense, it reminds you the Stewardson layer, maybe. And so it's actually quite natural. But there is some difference because here this layer is driven by the buoyancy force, but the very nature is about the same. So then other scaling is that d by dz, as we already solve with you on these interesting pictures. From the experiment, you see that there is almost no dependence in Z direction. And in this sketch, you see also again that there is almost no dependence in Z direction. So they elongated like that, but here in this direction, there is some concentration. So this is actually quite natural that the scale here is e to the 1/3. Okay, we considered that. So this value is of order 1. So this is a general view. And the solution then searched in the form. So we search for the solution. Actually, we can restrict ourselves by the Z component of the velocity in this solution. Then we have function psi. Another contribution of the stream function which we considered before. This is actually contribution from the first toroidal term. And then we can write down the general solution. Of course, it also includes tau, temperature variation. And we just represent it. Maybe better to write down that it's not equal, but just proportional, because it could be some proportionality coefficient, which generally speaking depends on some. So it's proportional to the exponent of I. And then there is constant K capital, which multiplied it by S. Then there is M, which is multiplied it by phi. And finally, there is omega. Please not mistake this omega with rotational rate. And so omega t. Okay. I don't know, man. Not to mistake this omega with the omega we have previously and the definition of Ekman number. Let's make it small omega. In original paper it was like that, but nevertheless it's better to represent as small omega. And in the result, what we have, in result with this is quite simple representation. So you just take the exponent, so you represent as harmonic function in cylindrical coordinate, in coordinate of azimuthal direction, and in the t direction we just have some engine value. No, with multiplied by I actually. This is the engine value because it's working like that. And so it's quite simple representation. Almost everybody knows such a representation via the expansion in cosine, sine, and exponent with corresponding function. So it's quite well known things. And again, I will not write down the equation. This resulting equation are on this slide, which we obtain substituting this in the previous equation, which is look like that, this previous equation. So we substitute this representation to this equation, and eventually the great advantage that we eventually have this system of the equation. Of course, I will not repeat it on Blackboard, it will be too lengthy. So we have this equation, this set of the equation, and the measure things for all this set is that we effectively removed cylindrical radius, azimuthal component, and time as well. We remove all this stuff from the system. And we keep only dependence on Z. Oh. I'm not sure that we will succeed. So, actually, as already told, we have this system, and here in this system, it's important to stretch out the relation between all these values which are listed on this page, and also there is the surface of the sphere which are at this place. There is also the A coefficient, which is actually represented like, I don't know. Okay, it's which actually this A coefficient is represented via the K, with this K. Then it's involved this M divided by S square, this S coming from here. But nevertheless, the most important message from this equation, first of all, of course, it's much more simple than initial one. This is, if our initial equation was equation of the second order for 3 variables, so now we effectively have the equation, each equation is of the first order, and for just one variable, just one coordinate. So actually we simplify the system a lot. And so then the next step is to estimate all this term of this equation in order of magnitude. And Bousset and Roberts did it in the following way. First of all, they estimated the Rayleigh number, because it's the most important number. And it's scaled like e to the minus 4/3 r. Oh, maybe I'll use the mouse, because there is a tendency when I have a screen, I want to point on screen. Okay, so we have this value, and here, okay, maybe I was wrong that you use small omega. Okay, just that. But you should distinguish this capital omega from the first omega which we used before that, because actually I don't know, it's such a bit mess with the notation, but you should be careful that then we have this scaling for all this value. First of all, there is a Rayleigh number which scale like e to the 4/3 of the r, which is the scaled Rayleigh number. Then we can represent this omega, which is responsible for the time period, like e to the minus 2/3. And then we can represent this value k, which is responsible for the cylindrical radius. It represents like this. And finally, we represent all the functions. So in the relative extent, that scale like this on the bottom. And then finally, we can rearrange this initial system, which I'll just already show, to even to more simplified one. And it's written here. And actually, almost the same system, but with some reduction. So then we proceed further. And eventually, all these three functions can be collapsed to just one, which is written here. And this is actually the things which constitute the deviation, constitute the simplification from the previous system. We just neglect by one contribution. Especially in this, on the last row, you see that there is no any derivatives, so it's the sort of the algebraic relations. And here you see also there is only one derivative, and only one here. So effectively, this is actually algebraic relation, and this one and this is the first order equation. So eventually, all this system becomes just the equation, ordinary differential equation of the second order, which is written here as 5.15. And we can even reduce this system further, and we reduce it even at the boundary condition, of course. Here there is the system itself, but below there is the boundary condition at one boundary and at another boundary, one boundary at z equal naught, and another boundary at z equal this value of the cylindrical radius, which could be on the top, then we have taken the plus, or on the bottom, then we taken the minus. And in this case, we apply this boundary condition. Okay. Okay. So actually, this simple formulation replace all we have from the very start, but there are very many parameters. Let's now consider all these parameters in this system. And of course, it's necessary to solve this boundary value problem for all these parameters, just taking on the value of all these parameters and estimated corresponding solution. So to construct the dispersion relation for our problem, we solve this two-point boundary value problem, this two-point boundary value problem, which is formulated here. 5.15, 5.16 for the complex eigenvalue omega. Here, this complex eigenvalue omega appear here, and even, it's not appear in the boundary condition, but it's appear here in the equation. And following the scaling, m is no longer restricted to be an integer, and it is straightforward to find omega for any value of the parameters using standard numerical techniques. The objective of the local theory employed by Roberts and Bousset is to maximize the growth rate. Actually, this is quite obvious objective. The growth rate, which is in terms of this omega, is imagined part of omega, and it could be maximized over all admissibly real s and k. S means the cylindrical radius, k means S means the cylindrical radius, this here, and k means the wave number in the phi direction. The imaginary models are then identified by the maximum value of Rayleigh number, which gives steady state solution. So this is the critical Rayleigh number which we necessary to find. Evidently, this local disturbance is natural, neither growing nor decaying in the space. And actually, imaginary part of K is the parameter which appear here, this K parameter, and it's is equal 0, and thus the later condition. So actually we define as we already told, we define this modified omega which comes from there, like the function of the following parameter. S cylindrical radius is plain like a parameter, then K, this is wave number which is plain in phi direction, M, and also we are using modified Rayleigh number. In all this parameter space, we are looking for the most highest growth rate and correspondingly for critical values. And the object of the local theory employed by Roberts and Bousset is to maximize the growth rate over all possible real values. The marginal modes are then identified by the minimum of value of the Rayleigh number R, which gives steady-state solution. Evidently, these local disturbances is natural, neither growing nor decaying, and corresponding imaginary part is 0. Thus, the later condition, this is, perhaps it's appears somewhere here. Okay, we have this. So everything we have on and expand the imaginary part of omega. Determining the Rayleigh number R and with frequency real part of omega in the terms of S, K, and M, like it's written here. So we use this equation, just equating to the maximum and then extracting from it the most suitable part of this modified Rayleigh number. So let us minimize R over n and fix it S and K. Then for an increment delta M, this increment delta M, which is shown here, we can expand it in this way. And since the minimum of the characteristic is characterized by the condition that the R is equal not, condition of critical are in total agreement. So there is a point where it's still in total agreement, but consider now minimization of over K and S by arguments similar to those used for 5.19, but involving increment decay and ds. Instead, we obtain the condition. So this is the point where there is a difference. This point states that we are developing the last two cases, And this is indeed the condition for the local theory. And this completes the determination of minimum RL or R over all real value of M and K and S. And the solution of the system of equation 518, this system of equation, and with the following equation, so solving all this equation, one of John's for the set of different Prandtl number. So this is the numerical result. You see that for different Prandtl number, we can estimate the result from the local theory. And here in brackets, you see the result from the direct numerical simulation. You see that there is rather big difference. For example, here from the local theory, we the number like this value, but in direct numerical substitution, we obtain sufficiently smaller value. And there is also some difference here. There is also some difference here, but frankly speaking, not so much. But if we raise the Prandtl number, so in this case, you see that the difference becomes more valuable. Maybe not so much different. And so actually this local asymptotic is, while could be re-estimated by the, could be accurate enough for our purposes, but still it's not so accurate as it required from the general and so exact theory. So perhaps we finished with this paper which named the local asymptotics. Then on the next meeting of us, we proceed to the global asymptotic. And now perhaps if you have some question, please raise them. The last line is that we are looking on the imaginary part of the derivatives of the omega, with this actually eigenvalue, in cylindrical direction, and on the condition that we keep this L constant. And under this condition, to reach the extremal point for the critical convection, we should satisfy zero. So this is the sort of the minimal maximal consideration which we are looking for just to identify the critical point.
Okay, sir. Thank you.
Okay, is there any more questions? Okay, I just draw the conclusion that this local theory, of course, not so correct, but it's still rather accurate. But nevertheless, to get the sort of the precise theory, we need to proceed further and to consider the global asymptotic, because this one is just local, and it's just give the extremum we are looking for at some local position in complex domain. But eventually, it was the big breakthrough that when we considered some global position in this complex domain, and it was done by the Jones, Stowart, and Ali Musa. Okay, so maybe. But the major advantage of all this stuff, as far as I could see, that we reduce very complicated system. You saw it. It was the system of actually 8 order in partial derivative in all three variables. But eventually we reduce it just to the one coordinate dependent. And there is no dependence of time because it's actually in engine value. And then we have a simple picture how this thing is operated, and actually almost for any case we can have almost exact solution. But to get sort of the exact solution, we should make the next step, which I report you tomorrow on about the global solution. So, in some sense, we finished. Is there any more questions?
Sir, previous slide. Can you? Previous.
One more question.
Previous. The scaling E equal to that Ekman scaling.
With scaling.
Scaling.
Okay.
Sir, here. Sir, how we can choose this type of scaling that R equal to R to E to the power?
Actually, we put this scaling when we. This is the initial system from which we extract this scaling. We just keep this term in each equation. We compare one term and another term. One and another. Sometimes we compare three terms. And to have the equation valuable, that it's not cancelled out.
Okay.
We suppose that there is balance between these terms.
Okay.
And first we suppose that these terms are in some arbitrary power. And then we just feed this power in the way that all these terms are balanced.
Okay.
So this is quite ordinary trick which we did with you.
You did
when
before.
estimated Stewardson layer. And so it's quite thing which is close to the estimation of the Stewardson layer we consider. And it's exactly e to the 1/3, like in Stewardson layer.
Yes. Yes.
So this is a quite ordinary trick, but not everybody plays that.
Okay. Thank you, sir.
Okay. One more question. Okay, perhaps we finish. Thank you for your attention.
Yeah. So today we are going to see in this tutorial class finite difference method and spectral method. These are the two things. Already we have seen finite volume method. Okay. So for that one again we are going to consider a computational domain like this. You can see now. So our computational domain consists of a rectangular region bounded by walls. So here we are considering stress-free boundary conditions. Not in the previous case it is rigid boundary conditions. Now we are considering here stress-free boundary conditions. Okay. Of course, these things are already elaborated, I think. So in this one, what is that? The temperature difference between the hot bottom boundary and the cold top boundary drives the flow. So this flow is driven by temperature. Okay, that is what it is given. And the left and right boundaries are insulated boundaries. Okay. 1 second. Okay, so yeah, side boundaries are thermally insulating, that is there is no heat flow through them. Fluid flow and the gradients only in two directions. That means we are assuming this axisymmetric case along the y direction. So only in the z and x direction. Now we are going to find out this flow with respect to the streamlines and isotherms. Already we come across about the streamline definition in fluid dynamics. How to write down? Let us see that. Next slides will tell you that. Okay, now the basic governing equations from the starting of the course we are seeing that the first one is by assuming the flow is incompressible fluid, not flow. Fluid is assumed to be incompressible fluid. So we come into this continuity equation of the form divergence of that velocity vector equals Kansas fluent, otherwise also open form, etc. You have to give the values in terms of the dimensions. Velocity meters per second, like that you have to give. Length in terms of millimeters, meters, etc. But here we are giving them in the non-dimensional form. How to non-dimensionalize? We are seeing every day, isn't it? Different scaling factors we are seeing. So this parameters also occurring in a different way. Okay. The next last equation is the heat equation, and again we have the nonlinear term there, isn't it? Right hand side first term is the nonlinear term. In this tutorial let us start with the linearizing this one. Okay. all variables are non-dimensional, and the domain is considered from x is varying from 0 to a, this one. You can see here, na, x is varying from 0 to a, and the vertical direction is varying from 1, 0 to 1, okay, 0 to 1. So we are going to give different values for a, and we are going to do we are going to simulate the flow here, okay. That is the idea behind this. And a is nothing but our L by d, where d is the depth, L is the length, okay, and a is known as the aspect ratio of the box. Usually in some papers they used to denote with gamma. Even in finite volume method also we have the symbol gamma is there, isn't it, along with the diffusion coefficient. Last one, del square V is there, last one, del square V bar, actually it is multiplied with gamma, okay. There in the finite volume method we have used, just to relate those two things I am teaching you like this, okay. Now already we have seen the basic definition of the Rayleigh number is given to be like this. G naught, that is G is a gravitational vector, it is a vector, and we are considering only in the z direction, and alpha is the thermal expansion coefficient, delta T is the temperature difference between the bottom and top layers, okay. Then D is the depth of the layer, and nu is the kinematic viscosity, kappa is the thermal diffusivity, okay, and PR is defined like this, okay. These are the basic things. Now let us move on. Now, so we are, as I said before, we are considering the linear stability here, okay. So as I said before, two methods, finite difference and spectral method. So finite difference is generally used everywhere. What is that? Numerical technique used to approximate derivatives by discretizing differential equations, the basic definition. So in linear stability analysis, finite difference method is applied to convert differential eigenvalue problem to a matrix eigenvalue problem, okay. So we are going to convert that to find out the stability of the flow, at which number, I mean the parameters, Rayleigh number and Prandtl number. Mostly Rayleigh number deals with the temperature difference, which exactly for what values the flow is becoming convective. Onset we are going to find out, okay, based on this eigenvalues. Now we are going to do that numerically. FDM also describes solving the equations computationally, okay. Now coming to spectral method, what it tells us, again we are solving the equations only by transforming them to a simpler form using basis functions. That means trigonometric functions we are going to use. We are going to rewrite this velocity dependent variable in terms of sine and cosines, that is trigonometric function, okay. Here it is given, the spectral method is based on Fourier expansions, okay. Let us see that how it has been written, okay. Coming back, we want to remove that pressure term, because for the pressure there are no boundary conditions, okay. How to deal with the pressure? To remove that one, we are going to introduce this vorticity vector, okay. It will already, vorticity is defined as curl of velocity, that is shown there. Then it is a two-dimensional problem, so we have that term. If you write down in this curl how to do, then you will get the values. Here it is shown. This is vorticity is given to be like this. Vorticity is defined in terms of the vectors like this. Vx is usually we denote u, Vy is v, okay, and Vz is w. Here we have considered only x and z. That is why u and u and w is appearing here. Vx and Vz. Any doubt in this slide? Okay. Now, based on that one, now what we are doing, as I said before, we want to eliminate the pressure. So what we are doing is we are taking the curl of Navier-Stokes equation, whatever is given, then it will reduce to, after some calculation, it will reduce to this form, equation 1.7. Now what is our aim? We are going to find out omega from this equation. Okay, from this equation we are finding out omega, and okay. After updating with the vorticity, fluid velocity is updated with respect to the stream function. Okay. How it is defined stream function? 1.9 tells here. Basic definition only. Velocity components u or vx equals to negative of dou psi by dou z, and we are choosing this stream function such that it satisfies the continuity equation. Okay, divergence of V bar will be 0. If you substitute that one, then automatically you will get, yeah, this one also. It will get satisfied. Okay. And what is the relation between vorticity and stream function is? It looks like a Poisson equation. So now we are going to find out the vorticity, stream function, temperature. Then from that, once we know vorticity or stream function, we can able to find out the velocity. Our aim is now to solve for the dependent variables, this one, vorticity, stream function and temperature. Okay. Now let us move on to the spectral method. Already we want to find out these three things. These three dependent variables, we are decomposing them into trigonometric functions, that is Fourier series. So you can observe here, this is a function of x and z. Already our domain is a rectangular domain. We have taken x-axis and z-axis, and also we are taking time also here. Now we are rewriting that in terms of the series form. Okay, Tn, again cosine is in terms of x, other two variables along with this. Okay, and n is varying from 0 to nn. How many grid points we are going to take? That much value here. Similarly, we are writing omega and psi here. We are choosing sine and cosine such that it will satisfy the boundary conditions. Okay, what is the boundary conditions here we have considered is stress-free boundary conditions. Okay, yeah. N represents the wave number of the Fourier modes. So how many modes we are going to consider, that much accuracy we can get. Yeah. So the truncation level, some more explanation for the notations here. Truncation level, this is the maximum mode number included in the spectral expansion. As I said before, if you include more number of modes, then accuracy will definitely increase, isn't it? N equal to 0 to nn here, you can go from n equal to 0 to 1 also. Then here T1, T0 z comma t cos n pi x by a plus T1 z comma t cos n pi x by a, like that we will get. Two modes, we call them as two modes, three modes, etc. Similarly for the vorticity and stream function. Okay, yeah. The temperature expansion starts with n equal to 0 because the cosine term for n equal to 0 is non-zero. If I substitute n equal to 0 here, you see, n equal to 0, cos 0, 1, that's what it is written here, represents the horizontal average of the temperature at the given vertical position z and time t. Only we have here the variable, if n equal to 0, temperature is a function of z and t only. If n equal to 0 here, vorticity and this stream function becomes 0 here, satisfying the conditions. That is what, okay, here. Next, n equal to 1 mode represents half wavelength that spans the length of the domain. So n equals to 1 mode. So for every mode we have an explanation. N equal to 1 mode represents half wavelength. Okay. Aspect ratio already we have seen, L by D. The length along the x direction divided by depth of that layer, depth of the that domain which we have considered. Next, wave number is defined as n pi by a. Okay. If we, how many modes we are going to consider, based on that, this wave number also differs. Okay. This represents the number of radians per unit length for a given Fourier mode. Okay. This is our language. We call modes, etc. here. Yeah. So insulating boundary conditions. Already we have seen, we are, and the side walls will have the insulating boundary conditions. That is what is given. Yeah. It is automatically satisfied by the cosine expansion of the temperature because the derivatives of the cosine expansions are 0. Left side and right side. X equal to 0 is the left side, x equal to a is the right side. Okay, aspect ratio. Similarly, impermeable condition. Then comes stress-free condition. How it is mathematically given here is represented here. Vx is in terms of stream function, it is given like this, and it should be the impermeable condition. That is, it vanishes. And the stress-free condition is, it is given like this. Mathematically, it is given. Okay. Coming to the next step, what we are going to use is here this condition, orthogonality condition. So sine n1 pi x by a, sine n2 pi x by a into dx, if n1 equals to n2, then it will have this value. Otherwise, if they are not equal, then it will have the 0 value. Orthogonality condition we come across about these two. Similarly, we are going to write down for the cosine function also. See here, for the cosine terms also. Here for the sine, next one is for the cosine. Okay, now what we are going to do here is the spectral expansions of T omega psi, that is the original equations. We have seen here, this one. This is the omega equation, and the temperature equation is, we started with that one, this one. And then T omega and psi. Okay, psi is, yeah, this one. The spectral expansion of this dependent variables are substituted. What are the spectral expansions? This one, this spectral expansion. Instead of T, you are writing them in the series form. Instead of omega, you are writing down that in the series form. Instead of psi, in the series form. Where? In the Navier-Stokes equation. Okay. You will land up the equations like this. Because you have to take the derivatives also. The partial equations have the derivatives also. You have to substitute them and you will land up like these three equations. These are the final equations. Okay. Now we are going to write down the code to solve this. To solve what? Temperature, vorticity and psi. Okay. So the boundary conditions also, how it should be written. That is what the explanation here. Isothermal boundary conditions means uniform. Iso means uniform, isn't it? Uniform thermal boundary conditions for the mean temperature perturbation T naught equals to 0. T naught means initial temperature. Initially it is 0 at Z equals to 1 and T naught equals to 1 at Z equals to 0. Z equals to 0 means bottom boundary. Then top boundary is Z equals to 1. Okay. For n greater than 0, Tn equal to 0 at both top and bottom boundaries. Okay. Next one is impermeable boundary conditions. So for all values of n, psi n will be 0. Both boundaries, bottom and top boundaries. Okay. The next one is stress-free boundary conditions. This also already I have shown, and we are writing in terms of this spectral expansions. Okay. Now Fourier coefficients Tn, omega n, psi n for n greater than 0 vanish at the top and bottom boundaries. Okay then. So you are going to write down that in terms of the Fourier expansions. The equations are written in terms of the Fourier expansions. That is like this. Now we are going to apply the finite difference method. Already we know what is a finite difference method. We are going to apply here central difference method. Isn't it? And this term will not be there because we are doing the linear stability analysis. So automatically we are taking out these two terms, this one and this term. Then how to write the finite difference method, isn't it? That we have seen in the finite volume method itself, that is the difference between the next step minus the current step divided by the grid spacing of delta T. Here you see, that is what it is written. Okay, this is the simple expansion for the using the Taylor series. Taylor series expansion by assuming the functions are continuous. Now that is what it is written here. For k plus 1, here k minus 1. Now adding and subtracting and doing some calculations, we can get first order derivatives, second order derivatives. That is what it is written. So first order derivative is, this is a central difference method. nodal point k plus 1 minus, not k, k minus 1 divided by 2 deltas. So this is a central difference method. Similarly, for the second order derivative also, central difference method is given. Now for the time, it is using this, what is the method? Adam, somewhere it is written. Adam-Bashforth method. Okay, using that one, time is discretized for all the dependent variables. It is, we want to know the value at the next time step. Instead of jumping too far, we are moving half interval, then again half interval. So t plus delta t by 2. Okay, that is what it is written. So it is the average of this one. 3 minus 2 divided by 2, so you will get back this one. That is the idea behind this. Okay, so we are substituting this one here and we are writing, see, delta t by 2, 3 gt minus g t minus delta t. Instead of t, we are going to substitute this t values, whatever we are going to know that. Yeah. So we are, till now we are dealing with this one, general finite difference formulation, and for the time. These things are for the space derivatives. Z is a space coordinate and t is the time coordinate. Okay. Next one, how to solve this Poisson solver. Because what is the formula we had? Omega equals to, omega equals to, where is it? Minus del square psi. How we are going to discretize this one? How we are going to discretize this one? Once we know the value of omega, we can know the psi value, we can go back, etc. Either psi or omega we want to know. Here. This is based on the spectral one. Already we have defined here. Here you see how omega is defined. You are going to substitute this omega and psi into that equations. Omega equals to minus del square psi. There you have to substitute these values and get this equation. And then for the derivatives you are applying the finite difference method. Okay. After this we will get the values at the nodal points k minus 1, k, k plus 1. How to solve that one? Using k minus 1, k, k plus 1. So tridiagonal matrix solver. Okay, that's what it is written. That is what it is written here. You see, subdiagonal, diagonal, superdiagonal. With this unknowns and right hand side is known values. Solve it and get the answer. Okay. So what are the coefficients also? It is written here. Yeah. Subdiagonal values, everything. Now the equations. Yeah. By neglecting the linear, non-linear terms, the equations are written here. These are the three equations already I have shown you with the conditions. Top and bottom conditions. Okay. Boundary conditions. Yeah. So up to this we are going to solve this one and we are going to see the solutions. The analytical solutions, if we do, we will get the critical numbers. Okay. Later once we finish this Fortran code, we will move to the analytical solutions, that is finding out the critical Rayleigh number if time permits. Okay. First we will do this one. The linear code is available, we will do that one. Okay. Already we have done some work. We will present that one. Let us see that whether online Fortran is working. If anybody has Fortran, it's okay. Otherwise also you can try this code in online. Online Fortran. Nowadays online C, online C++, Java, everything is available. Na? I remember I tried online also. Is there? No, we have done in Fortran this code. Say, okay then. Okay. Yeah, we will try that code now. Yeah. Okay, stop. Online Okay. So the how to apply to the code, how to do that one, then how to plot them. These are the three things we are going to do today. Okay. If you understand, you can go for the non-linear thing. This is only linear. Okay. Okay then. I'll try this. Yeah. Okay. Yeah, you open that PDF file, na? Can you open it? It's available there.
Good evening, everyone. I am Preeti. I am from SR University, Warangal. Now I am in the first semester of my PhD program. My supervisors are Dr. G. Ravikiran and the co-supervisor is C. Balarama Krishna. I'm just started my coursework. In my coursework, I'm studied about the biofluid dynamics and as well as numerical solutions of differential equations. I have not decided any particular program to in research, but I have a plan to do in the fluid dynamics with non-Newtonian fluid. Okay. Now I am taking one of the tasks given by the Sergi sir, that is 1.4.2. Here the momentum of equation and continuity equation is I am deriving here, that is this is the unsteady term, and this is viscosity term. Sorry, this is convecting term, and this is viscosity term, and this is density. This is the body force. This is my equation 1. This is the momentum of the equation, and second one is continuity equation. This is equation 2. Now given condition is U bar equal to omega cross R cross plus V bar. This is equation 3. Now I am substituting equation 3 into equation 1, that is though U bar is here, given condition, that is omega bar cross R cross plus V, that is dou by dou t, plus U bar is same, omega bar cross R cross plus V bar and nabla. Again U bar is omega cross R cross R plus V bar. This is the right hand term. The left hand term is mu nabla square. U is omega cross R cross plus vector V this is my equation 4. Expanding this, dou V bar by dou T plus dou by omega cross R cross by dou T plus V bar omega cross R cross plus delta plus omega cross R cross plus V bar cross V bar dot delta plus omega cross R cross now mu delta square this is equation 5. Now I am doing the cross product of this omega and R bar, that is this is in the z direction, that's why I am taking omega k, that is xy plus yj plus zk. This is the I and j will get k and I will get j. This is the opposite rotation will get minus, that is y I cross product, this is 0. Now omega cross R is I is here minus omega y and j is omega x and k term is 0. Now these equations I am substituting in. Now from equation 5, omega cross R cross delta V bar, we can, by solving we can write as omega V bar and V bar dot delta omega cross R equal to omega cross V bar omega cross R value is 0. These are substituting in equation 5. We'll get that dv by dt and here differentiating with respect to t, then we'll get 0, that is V bar plus delta V bar plus omega plus V bar plus omega plus V bar is equal to mu dot delta square minus gradient P plus density. Now that is V bar plus 2 the plus V bar equal to mu delta plus V bar minus delta P by F delta P. This is the required equation of the moment. Now I am deriving the continuity equation. We already given that mu bar is plus V, substituting is omega plus V equal to 0. Cross R bar plus V equal to 0. This term is 0. Final term is, this is the equation of the continuity.
Here, let's check the units.
Yes.
So here we've got dv over dt. Here we've got v nabla v, and here something bad happened.
From the we have substituted this equation in the equation 5.
Uh-huh.
This is from the equation 5. That is there.
Yeah, I got it, but maybe it's not plus here, because omega
Yes,
plus
yes,
v,
cross,
it's
cross,
yeah, it's
cross,
impossible. Just from from the consideration of dimensions. Yeah,
Cross
now it looks better. Now the dimensions are correct. Okay, okay, thank you. So by this, could you say some words by all these different relations and transformations? So what do we prove? Yeah. Continuity equation.
Continuity equation is
For another representation of velocity for a
Coriolis forces.
for a
Coriolis
Titan
forces,
system.
correct.
Okay, thank you.
Is there any questions? Thank you.